Hello and welcome back to Calculus 1, section 3.2, working with derivatives. So we are going to draw some conclusions and links actually between function and the derivative. We'll see which way they are related. I already said that derivative measures change. Worth writing it again. Derivative measures change. So, if I have a graph of the function which is constant function, say y equals 3, constant function, what is the derivative? What is the derivative of a constant? Y. Well, slope is 0, right? Vertical lines have no slope. This one does have a slope, but slope is 0. So you can think of it that way, sure. Slope is 0, we see that on our line, and derivative is slope of the line, so sure, it's 0. But we can also say derivative measures change. How much does the constant function change? It doesn't, right? So that's another way that you can reason the whole thing. So what is the derivative? In this case, it's just going to be right here. F prime of x is 0. Why? Because there is no change. It's constant. Now, if you have a function which changes, and I'm going to put some easy stuff. So let's start here at x negative 1, y 1. Thank you. I'm telling you I'm allergic at you, so still okay, yeah. I'm going to negative 1 to 2, 45-degree line up. Then I'm going to go straight to 5. And then I'm going to drop to 7. And stop. Black line is f of x. What is my derivative? What is my derivative? Very good. Derivative will be piecewise. Because we have 3 different pieces, they all have different slopes, which means the derivative will be all over the place. All right. What is the slope of the first line segment? 1. It's 1 unit up for 1 unit across. Slope is 1 over 1. Do we all know that the slope is rise over run from algebra? Thank you. Rise, up, run, forward. So you go 1 unit up, 1 across, 1 divided by 1 is 1. So, slope is 1. Now, what is the slope on the interval 2 to 5? It's a horizontal constant line. Slope is 0. Derivative is 0. And then, what's happening with the slope between 5 and 7? How much are we going down for going? Well, you have from 5 to 7, right? So you are forward in time 2 units. From 5 to 7 is forward in space 2 units. And what is your going down from this point to here? How many units? 4. So down 4 is negative 4. This is down 4. And this is to right. So what's the slope? Negative 2. It's a step function, actually, but it's a piecewise function. You have a piecewise function f of x, and you have the piecewise derivative f of x, prime of x. Another cool example to consider is absolute value of x. It's a v-shaped function. The function f of x is absolute x. What is the derivative? Anyone? Yes? These 3 pieces of line. It's a graph. Now we can make it into a function, but we are learning to spot it. So now what do we see on the bottom graph? What is the derivative? Anyone? This is why I'm depressed. He asks a question and 30 people go like, you know, whatever. And then obviously I have to feel alone and rejected. Talk to me, please. Where? To infinity. Good. So it's 1. How about the other part? Negative 1. Put one open circle, the other one closed, because you know you can't have both of them. So what's that in terms of our function? It's negative 1 for x is less than 0, and it's positive 1 for x is larger or equal than 0. That's our derivative. For absolute value. So black one is the function, red one is the derivative. Now, we are supposed to draw a conclusion here from this picture. Anytime function is increasing, the derivative is positive because it's above x-axis. Look at that. Every time the function is decreasing, the derivative is negative, which is below x-axis. So, decreasing f of x yields negative derivative. Increasing function or part of the function will give us positive derivative. So with this in mind, we take a look at the function 1 over x. Oh, by the way, the derivative preserves vertical asymptotes. I'll write that here. So we had a vertical asymptote at x equals 0. The derivative will have the vertical asymptote at x equals 0. That's fine. What kind of function is this? Increasing or decreasing? Decreasing. As you move from left to right, you are going down the hill all the time. So, you have negative derivative, but it curves, so actually the derivative will do the same thing. The other one is going to be this, because again it has to follow the vertical asymptote, and it has to be, derivative has to be negative because it's a decreasing function. Now, if you paid attention earlier, you can connect a lot of things with this example now. First off, 1 over x graphs this way. And now 1 over x squared graphs this way. But then 1 over x squared with a negative 1 on top flips the graph into what we have as the derivative. And this is the derivative. I think we did an example in a previous lecture. Did we do just the square root of x somewhere? I mean 1 over x? I think we did, right? No, we did 5 over x. Look what 5 over x gave us. Right? So if you just forget about 5, you get negative 1 over x squared. So we're good. So all of the concepts now kind of link over here. The black part of the line over here is 1 over x, and you have another one over here. They're both decreasing, expecting the derivative to be negative, which is below x-axis. The derivative has to follow the same asymptote, vertical asymptote, as the original function. Original function had the vertical asymptote at x equals to 0, so the derivative has a vertical asymptote at x equals to 0. So it should be natural that these guys have to sync in this way. Now, we calculated earlier that derivative is this. If you look at the original function, it has two of these guys looking up, but negative one over that looks like this. This is something that you learned in your pre-cal class. And look at that. That red is exactly that. Which is that. Flip of this. But that is the derivative of this if you calculate from the example that we had before. It's a lot of connections that you have to put together here, and they all work together. And that goes for all functions. So derivative definitely helps us figure out increase, decrease of the function. And in certain applications, you would rather look at the derivative graph than the graph of the function, because the derivative graph tells you how fast things change as well. I'm going to go back to this example where we jumped around. Observe that slower progression, which means slope was equal to 1 in this case, you get your derivative to be 1. This one, which is much faster change, has the derivative further away from x-axis. So as the derivative gets further away from x-axis, that means that the things are changing much faster. And when they're closer to x-axis, from whatever side, that means that the change is gradual, right? It's barely changing. So you can look at the derivative graph and come up with much faster interpretation of the situation, stock market, whatever, right? I mean, we'll see these examples as we go along. Finally, sketch the derivative. Sketch the derivative. And what's given to you is the function. All right. Let's all agree immediately that at the maximum point you have horizontal tangent line whose slope is 0. And at the minimum point over here, you also have a horizontal line whose slope is 0. Slope being 0 means that your derivative is crossing the x-axis. That's the slope being 0. We also know that when f of x is constant, there is no change. Therefore, the entire part over here has the derivative as 0. So I just need to fill in the blanks in between. Great. I need you to really see how cool this stuff is, because it fits so well every time. Look at this. If I draw these vertical construction lines over here, note that the function is increasing over here, decreasing over here, increasing over here, and it's a constant there. So we can draw the derivative in one shot. Increasing function means that the derivative is above x-axis, but it has to go through the point that I put right here, the point. It has to go through that point. So I'll draw something like this. Again, it's a sketch. It is not 100%. Decreasing part over here tells us that the derivative function must be under the x-axis. Well, wouldn't it be natural just to connect these two like that? The increasing part over here tells us that we have to be above x-axis, so yeah, right there. Cool? One more time. The increasing part over here tells me that the function is above x-axis, therefore the derivative function, right? That. The decreasing part over here tells me that derivative is negative, which means it's below x-axis. I have to connect those points. And the increasing part over here tells me it's above. This part over here is 0 because there is no change. And that's it. Now you can do this for anything. And the book has some really cute looking, well, I say cute looking, you might think diabolical, I don't know, problems. I'm going to put the vertical asymptote over here. I'm going to let the function have this piece. On the other side, it's going to go like this, and then end up being flat again. The first order of business when you have functions like this is to find min-max values. So this is definitely max, and I would say over here is a min. When you have min and a max, that gives you where the derivative crosses through x-axis. So you really have to identify those first, min and a max. Because when you have this, the tangent line through it is horizontal, slope m equals 0, but it happens only at that one point, and that's the reason why there is a point on the x-axis for the derivative. We have to honor the vertical asymptote. Vertical asymptote stays in the same spot. The easy part of the function is to put constant is the 0. So now, just connect the dots. The function is increasing, so it needs to be larger than, you can put any slope. It's a sketch, guys. It's a sketch, so I don't care how much you curve this. All right. It's a sketch. It's not precise. You're going to be precise in chapter 4. Right now, it's just a sketch. This piece over here is decreasing, meaning This. The next part is increasing and I have to obey vertical asymptote. So as this emerges, it will follow the asymptote forever. On the other end, I have increasing function. So which way do I draw? Yes, up. Nice, up. Do not memorize, oh, the function goes, you know, you have to think. This part of the function is increasing. And that implies positive derivative. And this is where the positive values are, above x-axis, right? Y equals 3, y equals 10, y equals 1,000,000. Those are positive values above x-axis. I talked briefly about the tangent lines. I set up the tangent line over here, right, for the zero slope. I want to know it because I want to smile too, but I guess not this time. There are these slopes here, and if you take a look, every slope I am drawing now has the positive value because all of the slopes rise to the right, and those are positive slopes. And the derivative in that respect must be also positive because the derivative consists of all positive numbers. Now I have to get rid of this clutter. You won't be able to see the picture. There we go. Good. So there is a link between the function and its derivative. See you next week. Good. I mean, technically that's it. Let's do one more example for you to practice. Again, sketch the derivative. I'll put 2 vertical asymptotes this time for double the fun. So this is f of x, the black one. These asymptotes are at -3 and 6, and this intersection here is at 2, doesn't matter. So work on this. I mean, good thing is that all of you have at least 2 color pens. You knew that you're supposed to bring in red today. Red crayon or whatever. So go ahead, try to draw that function. Now, this one is tricky, right? No min, no max. So that creates issues already. So let's see what we can do. There are no ways. Just guess. The only thing you can use is guess. Let's say ask everyone else because I haven't done it. All right, let's take a look together. Function is increasing, so derivative also has to be positive and above x-axis. So I'm just going to draw the piece going up right there. Now on the inside, function is increasing all the time, so the entire derivative has to be above x-axis, and on the last part function is decreasing, so it better be below. Got it? Right. Yes.
Why on the left it goes up, and on the right it goes down.
Is this increasing or decreasing? And decreasing means negative derivative. This is negative. It's below x-axis because all of the y numbers are negative. You can also think this way. Draw a slope tangent line. That was terrible. You should unsee that. All right. See that tangent line there? Has a negative slope, right? So m equals -3. M equals -3 is right there. And then the next point right there gives you this point. When you compute the slope is that value for the same x. You missed it. No, I just shut it by.